Let's have a look at the probability and counting technique. So we were looking at permutations, we were looking at combinations. Those exercises become a little bit easier because we know this is an exercise on permutations, so I'm doing a permutation. This is an exercise on combinations, so I know I'm doing a combination. When we mix it up, then we have to think for ourselves, hang on, is order important or not? So let's have a look at a few past HSC questions. This one from 2007. Mr. and Mrs. Roberts going to the theatre with their 4 children. How nice. I wonder what they're going to see. Maybe The Lion King. Anyway, they're randomly allocated 6 adjacent seats all in a row. And they simply want to know what's the probability that the 4 children are allocated seats next to each other. And so seats next to each other. Well, in this case, it's going to be a permutation because the order that they sit would be a different way that they could be arranged. So probability they sit next to each other. Bottom of the fraction, total possibilities, no restrictions. So that would be 6 people, 6 factorial. Top of the fraction, well, what have we got there? 3 factorial. The way of arranging 3 objects, 2 adults and 1 group of 4 children, because those 4 children, we're saying, hey, they're going to be together. So there's 4 factorial ways of arranging that little group. Once they've decided they're a group, it's like they're one person now. And so we have that group plus the 2 adults to arrange. And we get 3 factorial, 4 factorial over 6 factorial. Notice it's just 4 seats next to each other. They don't actually have to be in the middle of the 2 parents. 1 over 5 is the answer. All right, that's extension 1. Thought you might be interested in seeing extension 2. Because extension 2, one of the things they like to do is ask harder extension 1 questions, and one of the topics they love is permutations and combinations. So let's have a look at this one. A bag contains 12 red marbles, 12 yellow marbles. 6 are going to be taken out, no replacement. Probability that exactly 3 of the marbles are red. So probability that 3 are red. Okay, well there's my answer. A combination, because the order that I pull them out doesn't matter. I'm just getting 6 marbles. 12C3 times 12C3 on 24C6. Logic? 12 red marbles, going to grab 3, exactly 3. That means we need 3 yellow ones from the 12. Bottom of the fraction, no restriction. So of the 24 marbles, we're just going to grab 6, 24C6. All right, hence or otherwise. So they're giving us a bit of a clue that maybe this first answer is going to help us. Calculate the probability that more than 3 of the selected marbles are red. More than 3 are red. So if more than 3 are red, that means 4 are red, 5 are red, or 6 are red. Okay. So I could work out each of those individually, add them together. 4 are red, 12C4, which means the other 2 are yellow, 12C2. 5 are red, 12C5, 12C1 for the yellow. 6 are red, 12C6, and well, whether you put the 12C naught there or not, I suppose doesn't really matter. I mean, you're choosing no yellows. All over 24C6, and we get 0.32. But they said hence. I didn't use part 1. So there must be a way of doing this, using part 1. So here's the logic of how we tie in part 1. Probability of greater than or equal to 3 red, using the complementary idea, will be 1 minus the probability of 3 red, but also less than 3 red. Why write it like that? Right? Well, the probability of less than 3 red would be the same as the probability of greater than 3 yellow. And the probability of pulling out the red and the yellow were identical. So I can create an equation, because I can say greater than 3 yellow is the same as greater than 3 red. Move that to the other side of the equation. We just worked out probability of 3 red. So twice the probability of greater than 3 red is 1 minus the probability of 3 red, divided by 2, and we come up with the same answer. So that's how we can use our part A answer. So it's a nice little one. I'd love to know how many thought of doing it that way. Because it did say hence or otherwise. Remember, they did say or otherwise. So if you did do it the other way, that's still fine. All right, let's have a look at the 2006 one. This is a really interesting question, this one. Chess match between the home team and the away team. Game is played on 4 boards. So board 1, board 2, board 3, and board 4. Each board, probability home team wins is 0.2. Probability of a draw is 0.6. Therefore, that leaves us with 0.2 chance that the home team loses. The results are recorded by listing the outcomes for the home team. So if the home team wins on board, well, that should be board 1, shouldn't it? Home team wins on board 1, draws on board 2, loses on board 3, draws on board 4, we'd write it as WDLD. So just explaining the rules of the game for us. How many different recordings are possible? All right. Well, if you think about it, each board could either have a win, a draw, or a loss. So each board has 3 possible outcomes. Basic counting idea, 3 times 3 times 3 times 3 gives us 81 different possibilities there. Calculate the probability of the one that's recorded as win, draw, loss, draw. Okay, well, probability of win, 0.2, probability of a draw, 0.6, probability of a loss, 0.2, a draw, 0.6, 0.144. So far, question, not too bad. Now they add a bit to it. All right, teams will now score 1 point for a win, half a point for a draw, 0 points for a loss. What's the probability that the home team will basically wins? So scores more points than the away team. Okay. The way I thought I'd approach this, I said, well, first of all, I'm going to work out the probability that they score equal points. How could they score equal points? Oh, there could be 4 draws. So 0.6 to the power of 4. You could have 2 wins and 2 losses. That would give you equal points. So let me explain how this one works. Probability of a win was 0.2, so it's 0.2 squared. Probability of a loss was 0.2, so it's 0.2 squared. Now what's this 4 factorial and 2 factorial, 2 factorial? It's like saying, how many words can you make from the letters WWLL? Because that could be the arrangements of the boards. And if I'd asked you that question, you'd say, oh, 4 factorial over 2 factorial, 2 factorial, because there's 2 W's and 2 L's. So we get 0.0096. But there's also this possibility. 1 win, 1 loss, 2 draws. So 0.2, 0.2, 0.6 squared. But again, we could say, hey, how many ways could we arrange W, L, and D and D? We get 4 factorial and 2 factorial. Gives us 0.1728. I think that covers all the possibilities of getting equal points. So if we add that up, we get 0.312. So we know the probability of getting equal points is 0.312. Therefore, the probability of unequal points must be 1 minus that, 0.688. But remember, the probability of winning was the same as the probability of losing. So it's equally likely. So therefore, home team winning must be half of the probability of unequal points. Because half of those situations will be when the home team wins, half of them will be when it loses. And so we get 0.344 for the final answer. Let's say these extension 2 ones can be quite tricky. All right, what about this one? What have we got? 2002. You got 9 cards, conveniently numbered, 1 to 9. 3 are drawn at random, laid on a table from left to right. So in other words, it's like creating a 3-digit number. You just put the 3 cards down and it'll create a 3-digit number. Probability that that number exceeds 400. All right, well, what's the condition there? If it exceeds 400, the first number would have to be 4 or more. Okay. Well, 6 out of the 9. So that's all I'm really saying. Even though the whole thing's greater than 400, all I really got to say is what's the probability of the first card being bigger than 4? So 6 out of 9, 2/3. Probability that the digits are drawn in descending order. Now that doesn't necessarily mean consecutive. So you could go 9, 6, 2, but just the numbers are going down. I know total number of arrangements is 3 factorial. So I'll pull out the 3 cards and I'll arrange them. 6 different ways I could arrange those 3 cards. Of all the possible arrangements of those 3 cards, how many of them will they be in descending order? Yeah. So probability is 1 in 6. Yeah. It does not matter. I don't have to work out how many there are. I know it doesn't matter what I do. I'm always going to pull out 3 cards. Right? I don't need to know how many ways I can pull out those 3 cards because I know I'm always pulling out 3 cards. I just need to know how many arrangements of those 3 cards are in descending order.
So what are the 3 cards?
Because of every possibility that I could choose of the 3 cards, only one of the arrangements of those 3 cards out of the 6 ways of arranging them. Let's add 10H to our list.